All right, let's dive right in. Today, we're going to sharpen a tool that is the absolute foundation for some of the toughest problems you'll face in the IITJEE, set theory. Seriously, this isn't just another chapter to memorize. It's the language of logic itself, and mastering it will give you a massive edge.
Look, we get it. The IIT JEE syllabus is a mountain. You've got calculus, mechanics, organic chemistry. It all feels huge and honestly pretty overwhelming. The biggest question for so many people is just, where do I even begin?
Well, you begin right here. Because by mastering set theory, you're not just checking a box on the syllabus. You're learning the actual language behind functions, probability, and so many other topics. Think of it as the key that's going to unlock some of the most complex problems you'll come up against.
So, first things first, we've got to learn the vocabulary. Think of this next part as learning the alphabet before you can read the book of advanced math. We are about to turn all that chaos into some serious clarity.
So what even is a set? At its heart, it's just a collection of stuff. That's it, but it has two simple rules. One, it has to be well-defined, which just means we know exactly what's in and what's out. And two, the objects have to be distinct, no repeats allowed. For the IITJEE, we're usually talking about sets of numbers.
Okay, so you're going to see sets written in two main ways. The first is roster form. That's just a straight-up list of the elements. Easy enough. The other is set builder form, which is more like a rule book. It defines the property an element needs to have to get into the club. Both describe the exact same collection, just in a different way.
All right, we've got the definition down. Now it's time to build our toolkit. These three core operations, union, intersection, and complement, are the things you'll actually use to work with sets. And let me tell you, for the exam, mastering these is completely non-negotiable. First up is the union. The symbol kind of looks like a big U, which makes it easy to remember. Just think of it like you're merging two of your music playlists. The union is the one giant master playlist with every single song from both, but of course without any duplicates. You're just combining everything. Let's see how this works. Say set A has the numbers 1, 2, and 3. Set B has 3, 4, and 5. When you combine them, you just list everything out, 1, 2, 3, 4, 5. See how the number 3 was in both? We only write it down once. It's really that straightforward.
Next in our toolbox, intersection. This one is all about finding the common ground, the overlap. Back to our playlist analogy, the intersection is the list of songs that show up on both of your playlists. It's only the elements that the two sets share.
The key word to remember for intersection is and. We are looking for elements that are in set A and also in set B. So if we compare our two sets, 1, 2, 3, and 3, 4, 5, what's the only number that satisfies that condition? It's just 3. So the intersection is the tiny set containing only the number 3. And finally, we have the complement. This is basically everything else. It's all the stuff that's not in your set. Now here's the catch. To figure this out, you first need to define your universal set. That's the entire universe of possibilities you're even considering. The complement is just everything in that universe that isn't in your specific set.
Let's try it. Let's say our entire universe of numbers is just 1, 2, 3, 4, 5. And our set A is 1, 2, 3. So the complement of A, which we write as A prime, is everything in that universe that is not in A. What does that leave us with? You got it. 4, 5.
Okay, so we've got the operations. Now let's talk about the rules. And this is where it gets really powerful. Because these tools don't just behave randomly. They follow predictable rules, just like the algebra you already know. Understanding these properties is the secret to simplifying complex set theory problems on the exam.
Let's start with one you probably already know, the commutative property. All this means is that order doesn't matter. A union B is the exact same thing as B union A. Same for intersection. I mean, think about it. It doesn't matter if you combine playlist A with B or B with A, you're going to end up with the same master list, right? It's these reliable rules that make set theory so useful. All right, let's level up. We're going to talk about a concept that loves to show up in the trickier exam questions, the power set. This is a big shift because now we're not just thinking about the elements anymore. We're thinking about all the possible sub-collections or subsets you can create. The power set is literally a set of sets. It's a collection of every single possible subset you can make from your original set.
And you have to remember, this collection always includes two special cases, the totally empty set and the original set itself. Don't forget those two.
Let's just build one from scratch so you can see it. Let's say our set is just 1, 2. Step 1. You always start with the empty set. Got it? Step 2. List all the subsets you can make with just one element. So that's 1 and 2. Step 3. List the subsets with 2 elements. Well, that's just the original set, 1, 2. And that's it. The final result is a power set that has 4 elements, and each of those elements is a set itself.
Now for the magic trick. This is the crucial shortcut you absolutely need for the exam. You almost never have to actually list out all the subsets. If you just want to know how many there are, the formula is simple. It's 2 to the power of n, where n is just the number of elements in your original set. Just take a second and wrap your head around that. A small, simple set with only 10 items in it explodes into 1024 different possible subsets. That exponential growth is exactly why they call it a power set, and it's why this concept is so critical for probability and combinatorics problems, a huge part of the IIT JEE. And there you have it, the language, the operations, and the incredible power of set theory. You've just sharpened one of the most fundamental tools in your entire IIT JEE arsenal. So the only question left is, with this newfound clarity, what complex problem are you going to break down first?
Hey, welcome. Today, we're going to dig into the mental framework you need to bring order to chaos and just solve really complex problems. We are talking about the architecture of equivalence. So think about it. How do we make any sense of the world? I mean, we group things, right? We classify them. But what really makes a classification system logically sound? And this isn't just some abstract philosophical question. It's the kind of hardcore, rigorous thinking that's absolutely critical for tackling the kind of problems you'd find on an exam like the IIT JEE. You know, the entire structure of how we organize things logically, it really all rests on one simple foundational idea, and that idea is called a relation. In the world of math, a relation is just a rule. That's it. It's a simple rule that defines some kind of connection between different items in a group, or what we'd call a set. Now, I know this might sound a little abstract, but you're actually using relations all the time. The rule could be is greater than when you're looking at numbers, or is a friend of when you're talking about people, or even something like is the same color as for a pile of clothes. See? They're all just simple rules that connect things. But here's the big question, right? Not all relations are created equal. Some are kind of flimsy. Others are rock solid. So how do we know if our rule, our relation, is actually strong enough to create distinct, non-overlapping groups? How do we know it won't just fall apart when we really look at it logically? Well, for any relation to be considered, let's say, a master classifier, it has to pass a super strict 3-point litmus test. If it fails even one of these checks, nope, it's not up for the job. So these 3 tests are called the reflexive, symmetric, and transitive properties. Think of them as hurdles. First up, the reflexive hurdle. Is any given thing related to itself? Second, the symmetric hurdle. If A is related to B, does that mean B is also related to A? And third, the transitive one. Does the relationship carry through a chain, like from A to B, and then from B to C? Now, a relation that actually manages to clear all 3 of these hurdles, that is reflexive, symmetric, and transitive, it earns a very special name. It's called an equivalence relation. And this is the gold standard, the ultimate tool for sorting things into perfect, well-defined categories. Okay, theory's cool, but let's put this to the test with a classic example from geometry. Let's imagine our set is just all the possible lines you can draw on a flat plane. And our rule, our relation, is going to be is parallel to. All right, let's start the test. First hurdle up, the reflexive property. The question's pretty simple. Is any single line parallel to itself? And the answer is yes. By its very definition, a line is always parallel to itself. So boom, it clears the first hurdle. Test 1, passed. Okay, on to test number 2, the symmetric property. This basically checks if the relationship is a two-way street. So if line A is parallel to line B, does that automatically mean line B has to be parallel to line A? Absolutely it does. Being parallel is a mutual thing. It doesn't matter which line you say first. So it clears the second hurdle, no problem. Test 2? passed. And now for the final and often the trickiest test of all, the transitive property. This is like the domino effect. If we know line A is parallel to line B, and we also know that line B is parallel to line C, can we then say for sure that line A must be parallel to line C? And once again, it's a huge yes. That property of being parallel just gets carried right down the chain, so it passes the final crucial test. So just look at that, a perfect clean sweep. Our relation is parallel to, passed the reflexive test, it passed the symmetric test, and it passed the transitive test. It went 3 for 3, clearing every single hurdle we could throw at it. So what's the big takeaway here? Well, because it passed all 3 of those tests, we can officially declare that is parallel to is an equivalence relation. It's earned the title. And this is where the real power comes in. An equivalence relation works like a perfect sorting machine. It can take that total chaotic mess of all possible lines and partition them into these neat, totally separate boxes. You get one box for all the horizontal lines, another one for all the vertical lines, another for every line at a 45-degree angle, and no line can ever belong to more than one box. That right there, that's perfect logical classification. And that, well, that brings us right back to where we started. Getting a handle on this logical architecture isn't just about memorizing stuff for a math class. It's about training your brain to think systematically, to test your assumptions, and to build solid arguments from the ground up. It is exactly this kind of structured thinking that lets you break down and just demolish those intimidating problems you'd find on an exam like the IIT JEE. So I'll leave you with this thought. How do you organize your own life? I mean, when you group people by has the same last name, or clothes by is the same color, or maybe songs by the same artist, you're using this exact logical architecture. So what hidden equivalence relations are you using to bring some order to your world?
So what if I told you there's a single, simple idea that connects that vending machine in your office to, the laws of gravity? I know, sounds a bit out there, right? But it's one of the most fundamental concepts in all of math, and it literally runs the world in ways you probably don't even see. Today, we're going to pull back the curtain on the function. It seems like a pretty weird question, doesn't it? I mean, on one hand, you've got a machine that gives you delicious snacks. And on the other, you have a math concept that, well, let's be honest, usually just gives you homework. But believe it or not, they operate on the exact same core principle.
And there it is, functions. That's simple, predictable logic. You put something in, you get something specific out. That's the absolute heart of what a function is. And we're going to use this whole vending machine idea to make it all make perfect sense. All right, so let's dive in with the absolute basics. Every single function, no matter how ridiculously complex it looks, follows a very simple set of rules. Think of this as the basic rule book for how they work. Okay, I know, the formal definition can sound a little academic, but here's the deal. You only need to zoom in on 3 keywords, exactly one output. That's it. That is the absolute golden rule of functions. For any input you give it, you get one and only one result back. It's all about rock-solid predictability. So let's bring this right back to our vending machine. The buttons you press, that's your collection of inputs, or what we call the domain. All the snacks sitting inside the machine, those are all the potential things you could get, the codomain. And the function itself, well, that's the machine's wiring. It's the rule that connects each button to one specific snack. And here is that golden rule in action. A working machine is a perfect function. You press A1 for chips, you get chips, every single time. It's predictable. But what if you press C3 and sometimes you get a soda and other times a candy bar? That machine is broken. And in the world of math, that relationship is just not a function. One input, one predictable output. That's the whole game.
Okay, so we've totally nailed the basic rule. Now let's level up a little bit. See, not all functions are created equal. Some of them follow extra rules that give them some really special, super useful properties.
First up, we've got the one-to-one function. And the name really gives you the biggest clue here. It means that not only does every input have just one output, but every output comes from just one unique input. No 2 inputs are ever going to lead you to the same result. Let's go back to our trusty vending machine. For it to be one-to-one, it would mean that the button for chips only gives you chips, and no other button on that entire machine will give you those exact same chips. Every single snack has its own personal, dedicated button.
Next, let's talk about the onto function. Now, this one isn't so worried about inputs sharing outputs. It's all about making sure that every single possible output is actually used. Nothing gets left behind.
So, in our machine, this just means there are no snacks sitting there on the rack that you can't actually buy. Every item listed as a potential output, that code domain we talked about, has at least one button that gets you to it. The entire machine is being used, top to bottom. I know these two types can feel a little similar, so let's put them right next to each other to really nail down the difference. It's all about the subtle but really important distinctions in what they're trying to do.
Here's the easiest way to think about it. One-to-one is all about exclusivity. No sharing. Two different buttons can't give you the same snack. Simple. Onto, on the other hand, is all about coverage. It means every single snack in that machine is reachable. And you know, what if some snacks are unreachable? Well, we call that an into function. It just means there might be a few things on the shelf that you can't actually buy. And honestly, most functions you run into are into by default.
All right, now for a really cool idea. What happens when you start linking functions together? This is what we call composition, and it's basically like creating a little assembly line, where the output of one machine becomes the input for the very next one.
So, the most important thing to get here is that you're not just running one process. You're taking the result from your first function, and you're immediately plugging it into a second function as its brand new input. It's like a chain reaction.
Okay, imagine a super fancy prize machine. You press a button, but instead of a snack, it pops out a special token. That token, that's the output of your first function. You then take that very token and use it as the input for a second machine. The awesome prize you get at the very end is the result of the composition of those two separate functions working together.
So we've had some fun with our vending machine, but why does any of this stuff actually matter? Well, because this simple logic of input rule output is, and I'm not exaggerating, the language of the modern world.
Just think about it for a second. Every single line of computer code you've ever interacted with, it's basically a function. The secure encryption that protects your bank account online, that has to rely on special one-to-one functions, because every unique piece of data has to encrypt to a unique code. Otherwise, how could you ever reverse it reliably? From data scientists predicting what you'll buy next, to physicists mapping the path of a planet, it is all built on this fundamental idea of a predictable relationship. So, I'll leave you with this thought. Our world is built on this invisible network of functions, from something as massive as the force of gravity to something as personal as the algorithm that decides what you see on social media. The next time you see a clear cause and effect, a reliable input leading to a specific output, just ask yourself, what's the function at play here? Thanks for joining this explainer.